Hello everyone, my name's Avyay Kolhatka and today I'll be presenting with my colleague Toby Carman on the comparison of fixed threshold CFAR and CNN ship detection methods for S-band NovaSAR images. For a bit of background, we both work at DSTL in the UK. The work undertaken sits within the Space ISR Project within the DSTL space program. The project has three key goals: to assess the feasibility of mission concepts and provide evidence-based support to future procurement decisions, to support the development of low-maturity, novel technologies that have defense application, to explore the existing cross-domain technologies that can be leveraged for improved ISR. NovaSAR is a S-band synthetic aperture radar demonstrator built by Airbus, mounted on a SSTL bus. Built as part of an initiative by the UK Space Agency to stimulate growth of the small satellite market in the UK. Launched in September 2018 on a PSLV into a sun-synchronous orbit at approximately 580 kilometers, its key applications are land use mapping, disaster management, and maritime applications. In this presentation, we will focus on the latter. NovaSAR has a resolution of 6 meters in Stripmap mode and a novel maritime mode with a 400 kilometer swath and 14 meter resolution approximately. This mode is suited for open water maritime environments. The satellite has an onboard AIS receiver for better maritime monitoring, and some UK maritime security applications include monitoring of UK exclusive economic zones, illegal fishing in British maritime protected areas, and sea ice monitoring to enable safer traffic at high latitudes. There are currently many ship detection tools available and many papers that look at the performance of CFAR and CNN for SAR imagery. This study focuses on the performance of these tools for the maritime application of S-band imagery. We discovered the nuances in each approach and the suitability for high data volume processing against ad hoc requirements to enable better procurement decisions and a better understanding of the state of the art in industry, with the ultimate goal of saving the analyst time and providing quicker, usable input. Now I will discuss the implemented fixed threshold CFAR. CFAR, which stands for Constant False Alarm Rate, is a well-understood method to detect ships in SAR imagery. The first step was to apply a landmask. This is critical in the event of poor geolocation. In order to do this, I first applied a Gaussian filter to smooth the image without removing the sharpness of edges. This can be done in conjunction with a reduction in image resolution or as standalone pre-processing. I then applied a canny edge detector and subsequent morphology to join and fill the holes in the land regions. Finally, I used segmentation techniques to create a binary mask. I then used the distribution fitting algorithm to identify the best fit to the empirical data. I used the gamma, log normal, and K distribution, although these could be extended to any number of existing distributions. The more distributions that the model cycles through, the higher the processing time. I then used the best fit to find a threshold by setting a fixed probability of false alarm ranging from 10 to the minus 4 to 10 to the minus 6 and measuring the error in the pixel intensities. Applying the threshold and selecting a minimum acceptable vessel size yielded a detected ship in the image as a result. The left-hand image shows a landmask applied to a lower resolution image. The right-hand image shows a higher resolution image with the littoral region showing more vessels. The trade-off is to be made here based on the application, the volume of data, and the timeliness requirements. Here you can see the detections for a 6 meter resolution Stripmap image. The red markers indicate detections, and it can be seen that there are many detections in littoral regions due to an effective landmask being applied. If we zoom in on the bottom left, you can start to see individual detections with red markers defining the detected centroids. Some vessels that have low reflectivities have not been picked up by the detector. Some objects in the sea that might be under the threshold size required to be identified as a ship have not been picked up as vessels either. The next results show for a ScanSAR image of 20-meter resolution. You can see that the reflectivity of the sea state is much higher in the near range at the bottom of the image than in the far range at the top of the image. This varying sea state means that applying a fixed threshold is an ineffective way of detecting vessels. The bright sea reflections in the near range created a huge number of false alarms and reduced the precision of the overall detection. It's clear that in this case, an adaptive threshold would need to be set with a sliding box that goes across the swath of the image to vary the threshold as the intensities are lowered. The output from the model was in the form of a CSV file with corner coordinates of the vessel bounding boxes. Many instances created multiple boxes for different parts of what can clearly be seen as a single ship. This penalized the performance of the detector when compared with the CNN method. Work is to be conducted on using Euclidean clustering to remove duplications in future applications. With that, I'll pass it over to Toby to discuss the CNN approach.
Hi, my name is Toby and I'm going to be talking about the alternative convolutional neural network method of ship detection. This approach to object detection has grown in popularity in recent years due to advances in graphical processing power. In this study we focused on detecting ships, so trying to find where they are located. We didn't attempt to classify, so that's a case of distinguishing between different types of ships such as fishing vessels and oil tankers. And indeed other marine objects such as wind farms and oil platforms. This was dependent on first training the neural network on a large dataset of labeled images. So in order to understand this, we first need to go over some of the performance metrics. Precision is equivalent to asking how many of the detections that we've made were actually ships. Recall is kind of the reverse, so how many of the ships in the image were actually detected. An F1 score is the harmonic mean of the two, so it's combining the two into an overall metric to determine how good the performance was. Mean average precision is another metric which tends to get used in the object detection field for multiple classes, but in this single class problem, it doesn't seem to be as useful as a metric. So RetinaNet was trained with the ResNet 50 backbone on the open source SAR ship detection dataset, which will be referred to as the SSDD. This saved a lot of time as the images, over 40,000 individual images, had already been labeled. The SSDD images were then randomly split into training, validation, and test. And the NovaSAR dataset was constructed and labeled. Two of the images from the NovaSAR dataset were removed to form test set B for comparison with CFAR, so that those two images would be completely unseen by the network. The remaining images were then segmented and split again into training, validation, and test, as with the SSDD dataset, and this 10% test split will be referred to as test set A. As mentioned, due to the large sizes of the NovaSAR images, it was first necessary to segment them into tiles in order to avoid downscaling and therefore a significant loss of detail in the images, potentially resulting in reduced detections. This shows the process that was used to segment the images. You can see that as the window slides across the image, there's a small overlapping region on the top, bottom, left and right of each image, which ensures that even if a ship in the image is slightly cut off by one of these tiles, it would be fully captured in the next tile and would have a full detection in at least one of these tiles. So in order to train the model, we first started with the generic ResNet starting weights, and trained on the 30,000 images found in the training portion of the SAR ship detection dataset to produce the SSDD trained model. The NovaSAR dataset was then incorporated, training on the 600 images from the training split to produce the NovaSAR trained model. Here we can see results for both models on the sets of image tiles. On the left, the SSDD model is able to detect 95% of the ships present in the SSDD test set with a precision of 85%. When the SSDD model was tested directly on the NovaSAR test set in the middle, performance was reduced as expected. However, 46% of the ships were correctly detected with a precision of 77%. The NovaSAR trained model demonstrated improved performance in NovaSAR images on the right compared to the SSDD model, detecting 74% of the ships present with a precision of 90%. It's expected that with a large enough training dataset, recall could be improved to match or even outperform the SSDD results seen on the left-hand side. In order to produce a set of detections for the entire image to compare directly with the CFAR method, it was first necessary to remove any duplicate predictions from the common overlapping regions between adjacent tiles. So to do this, the tiles are overlaid in their original coordinate space, and duplicates with the smallest area are removed. Here we can see a set of detections in the Stripmap image. We can see in the orange the detections, and in the blue is where we've got a label. So the blue can be considered the ground truth. We can see a small number of false positives over the land region, but a good level of agreement between the detections and the labels for the ships, with a high level of prediction confidence for most of these. In the ScanSAR image, we can see again a large number of false positives over the land-based region which has not been masked out, but a good level of agreement and high prediction confidence for the ships that are present in the image. We're now going to see a comparison between the two methods. So in the Stripmap image for test set B, all methods give reasonable levels of detection performance. The CFAR performance can be seen on the right, with precision, recall, and F1 score just below 50%. For the neural network-based methods, from left to right, the SSDD trained model without a landmask slightly outperforms the NovaSAR model in terms of F1 score, however the recall is greatly reduced. By slightly reducing the confidence level required for detection and introducing a landmask, as can be seen in the third set of results, the SSDD model's recall improves without detriment to the precision. Application of a landmask to the results derived from the NovaSAR model removes a large number of false positives without affecting the recall, with almost 80% of the ships present in the image being correctly detected. In the ScanSAR image, the CFAR method was unable to produce a usable set of detections due to brightness variations across the image. We can see that overall detection performance is reduced compared to the Stripmap image. However, introduction of landmasking does produce a usable set of detections using both the SSDD model and the NovaSAR model. The NovaSAR model can be seen to outperform the SSDD model in recall, though the precision of the SSDD model is slightly improved. One of the main findings is that, based on the good levels of detection performance seen in the results from the SSDD model, a user could exploit a neural network which has been trained on an existing dataset to extract value from a new mission on day one of operations, without the need to first build up a training dataset. However, incorporating some native data can further improve detection performance. Finally, both of these approaches have been shown to outperform a fixed threshold CFAR algorithm. So in this study, we used a fixed threshold CFAR algorithm. In the future, it'd be useful to compare to an adaptive threshold. We'd also like to incorporate negative examples into the neural network training, potentially include simulated data in training, investigate the robustness of both methods to adversarial attacks, investigate assisted labeling using AAS data, determine the most useful polarization, so HH, HV or VV, or potentially combining all three into a triple channel mode, and apply SAR-specific image augmentation such as speckle filtering and multi-looking. Thanks for watching. I hope you enjoyed the presentation.